Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to go over Le Chatelier's principle and the effect of temperature. So up until this point we've been talking about the effect of concentration and the effect of volume or pressure on the reaction. And none of those disturbances or changes have led to a change in the actual equilibrium constant. So the equilibrium constant has always stayed the same, assuming that we've been under the same temperature the whole time. So when you add your more reactant, right, if you increase the concentration of reactant, then it's going to shift to reduce that reactant. And then, but the at equilibrium, once you hit equilibrium again, the concentrations are always such that they would equal the reaction constant when you put them into the equilibrium constant expression, right? So that expression of K. Okay, but in this case, we're going to be changing the temperature and looking at the effect of temperature that it will have on the shifting of the reaction based upon Le Chatelier's principle. And in this case, the change in temperature will have an effect on the equilibrium constant. You will not have the same equilibrium constant. So let's get into this. So first, we need to remember what exothermic and endothermic reactions are. And so when you have an exothermic reaction and you have an endothermic reaction, an exothermic, exo means out of, therm is referring to heat or energy. So here, exothermic reaction is where heat is going out of the reaction. Heat is being given off. So here's a generic expression of a exothermic reaction where you have uh, reactants A and B react together to form C and D, and heat is produced from that reaction. And here's an example of an actual exothermic reaction where you react nitrogen gas with 3 hydrogen gas molecules to get to ammonia. And so that's going to release some heat. And endothermic is the opposite. So endo means into, and again, therm is heat or energy. And so here, heat is going into the system, so it's being absorbed. So here, you have reactants A plus B, and it's taking in some heat in order to form products C and D. And so here is another example of an actual problem or reaction that is endothermic. So here we have N2O4 gas takes in some heat, right? Absorbs some heat in order to form 2 molecules of NO2 gas. So this is an example of an endothermic reaction because heat here is absorbed. So you could think of heat as a reactant here. And so for this reaction, for exothermic reactions, you can think of heat as a product. And so for understanding the effect of heat on the equilibrium of a reaction, it's good to think of the heat being a product in exothermic reactions and heat being a reactant in endothermic reactions. And so if we remind ourselves about K, so remember that K, the equilibrium constant, is equal to, generically speaking, in a very general way, is going to be the concentration of products over the concentration of reactants. And of course, those products and reactants are multiplied together. They're raised to their coefficients as powers of the coefficients. But to make this simple and more easy to understand, we're just going to say it's concentration of products over the concentration of reactants. And so in previous videos where I was talking about changing the concentration, Le Chatelier's principle says that the system in equilibrium is going to shift in such a way to minimize that disturbance or that change or that stress, right? So when we're talking about changing concentration, right, if I add more A to this reaction, then it's going to shift in the direction towards the product. Why? Because it wants to get rid of the A that I added and therefore create more product. So what happened in the beginning? So when I add concentration, I increase this and therefore I changed the ratio here. Now what the system is going to do is going to shift in order to get that ratio back to the way it was to get your K value that was the same. So we're assuming same temperature here, right? So the initial disturbance was a disturbance that changed the concentration. Same thing with volume, right? So with volume, if I change the volume, right, if I make the volume smaller, I'm effectively changing the concentration. Why? Because concentration can be defined as the amount of stuff in a given volume or space, right? So if I decrease the volume, I'm effectively increasing the concentration because more particles are going to be given in a smaller space. Or it's this, even though it's the same number of particles, the concentration within that space is going to be more, right? So the number of particles in a given amount of space will be more because there's less space to fit those particles. So when I decrease the volume of my container and I'm squeezing those particles into a smaller space, I'm effectively increasing the concentration. So what is the system going to do? It's going to shift in a direction in order to lower that concentration or reduce the number of particles. So that was what was going on when we were talking about the effect of volume or pressure on the system. But here, we're not changing any concentrations, right? All we're doing is we're changing temperature. And temperature doesn't initially change concentrations of stuff. So what's going to happen is if we think of heat as either a product or a reactant, if we raise the temperature, what happens to the amount of heat? So think about raising the temperature. What must you do to raise the temperature? You've got to add heat, right? So you got to heat it up. So when you put heat in, you're raising the temperature. So if I think if I have an exothermic reaction, let's take exothermic reaction. So heat is a product. So if I'm increasing the temperature, right? I'm not doing anything to the initial concentrations. The initial concentrations are what they are, right? But I'm increasing, let me use a different color. So if I'm increasing the heat, right? If I increase and add heat, if I increase the temperature, that's like adding more heat. And so if we think of heat as a product here, it's like I'm increasing the product heat when I raise the temperature. Well, what is the system going to do if we think of it that way? Well, as we said before, with increasing concentration, it's going to shift in the direction to lower that amount of product. So if I increase the product heat by increasing temperature, it's going to shift in that direction in order to decrease or absorb some of that heat that was introduced and bring the temperature down. So it's going to try to absorb some of that heat. And so by doing so, it's going to shift in this direction. Well, if we didn't do anything to the initial concentrations here, well, these concentrations are now going to change because of the heat. So once the system reaches equilibrium again, then the initial concentrations are going to be different from what they were before. And so now we've changed the equilibrium constant. So again, let's say that we were at, for the sake of argument, let's say that the K value is equal to 2 and our initial concentrations were 4 and 2 for our products and reactants. Let's just say that's what we started with. Simply by changing the temperature, if I increase the temperature, I'm increasing the heat. That's going to cause, by Le Chatelier's principle, to shift the reaction more towards the products to get rid of that heat. Well, the addition of heat doesn't affect the original concentrations. So by increasing heat, I'm causing the concentrations to change for my products and reactants until equilibrium is reached again. So I'm going to lose product and I'm going to gain reactant. What happens to the product? That's going to go down. The reactant increases. So what happens when that happens? So if I lose two of these, right? So if the product goes down, maybe it goes down by 2, and the reactant goes up by 2. Now I've reached equilibrium again. So now this is at equilibrium because it's reduced the heat. But now look at my numbers. The numbers at equilibrium are now 1/2. So this is the new equilibrium constant under the condition of raising the temperature to, say, from 25 to 30 degrees. So now at 30 degrees, the equilibrium constant is now 1/2 instead of 2. So, and all of that is because I've raised the temperature to a higher temperature. So under those conditions, it's going to shift this way to decrease the equilibrium constant. So the equilibrium constant is going to decrease when I raise the temperature for an exothermic reaction. It's the opposite if I decrease the temperature. So if I use blue for decreasing, so if I decrease the temperature, then that means that in order to change this or fix this this disturbance in the system or a disturbance in the force, um, it's now going to shift in this direction in order to produce more heat to try to get that temperature back up, right? So it's going to shift in this direction now. So now instead of, if we start at 4/2 again, we're going to shift in the direction to create more product. So the product is going to increase. So let's say I lose one reactant and I increase product. So that means that now let's say that I lose a reactant and I increase product. So maybe this goes up to 5 and that's to a 1 now. So now you can see, let's say that's what happens when it reaches equilibrium. Once it reaches equilibrium at this new temperature, after I've lowered the temperature, now my reaction, the equilibrium coefficient, the equilibrium constant is now 5/1. So notice that the equilibrium constant has now increased because of this shift due to decreasing the temperature. So this is a good example or I guess a good example of what happens when you increase or decrease temperature for an exothermic reaction. It's the opposite of or an endothermic reaction. So everything is the same as we've talked about. The principle is the same, except for now we're going the opposite directions when we're increasing or decreasing temperature. So if I erase this here, right? So if we're now looking at our endothermic reaction, heat is a reactant. We're thinking of heat as a reactant. So in this case, if we increase heat, right? So if we, let me use red for increase. So if we increase the amount of heat here, right? So we're increasing heat here, or I guess another way to put it is we're adding heat. So we're adding heat in, so we're increasing the heat here. So what's the system going to do? It's going to try to decrease that heat. So we're thinking of this as a reactant. So if we're adding more heat, that's like adding more reactant. So what is the system going to do? It's going to try to remove that heat by absorbing it and going in that direction. So in this case, the amount of product would increase while the amount of reactant would decrease. And so in this case, again, we're increasing product, so product is going to go up, and we're going to decrease reactant. So if, let's say, if we take one reactant, make it a product, and so we get 5/1. So let's say it's going to shift in this direction to reach equilibrium. Once it reaches equilibrium, again, the equilibrium constant has changed. It's now 5. The equilibrium constant has increased in this case rather than decreasing. So for an exothermic reaction, increasing the temperature caused the reaction to shift this way and therefore decrease the equilibrium constant. For an endothermic reaction, raising the temperature caused it to go towards the products and therefore increased the equilibrium constant. So increasing the temperature has the opposite effect on an exothermic reaction as it does on an endothermic. So if we look again at decreasing temperature, so here if I decrease temperature, if I take heat out, if I remove heat, right, then what is the system going to do? It's going to shift in the direction to produce that heat, to try to go back to the way it was, right? So here it's going to shift in this direction, right, to make more heat because of the heat was lost. So we're treating heat again as a reactant. So same thing, if you remove reactant, it's going to shift to try to produce more of that reactant. But our reactant here is heat. So in this case, what would happen is instead of increasing the product, we're going to shift in this direction. We're going to increase reactant and decrease product. So in this case, we might lose 1 or 2 from the top. So we lose our product, so maybe that goes down to 2, and we add 2 to the bottom, and that becomes a 4. And so that's 1/2. So again, K would be decreased in this case. So that's the effect that it has. So I hope this is helpful. So we can see that when you change the temperature of the system, it's going to shift in such a way in order to relieve that stress. And that how it shifts is going to depend on whether it's an exothermic or endothermic reaction. And when it does shift, the new equilibrium constant is going to be different from the previous one. And so I hope this is helpful. If you enjoyed this video, if this was insightful and you learned something from it, so please like my video, hit this like button right here, like button right there, smash it. Also subscribe to my channel, hit the notification bell right up there, and put a comment in the comment section down below. Let me know what you think. If you have any questions that I can answer, let me know. Thanks for joining me. Have a great day.